all of a sudden the speed of sound somehow becomes so slow. So every communication, it takes, just time to just communicate.
Yeah.
So if you want real-time discussion, I don't know the overhead we need here.
Mm-hmm.
So do you see one participant called the physics department? And this is our new building.
Sorry, what?
So actually this picture of physics department, which is first, is our new.
Yeah, it's your new building. Okay.
Yeah. So probably you knew our old building. Did you visit?
Yeah, not recently, I guess, but.
Well, of course, it was standing, and it was Carl Cave's dream to have a new building before he retires, and it barely happened.
How new is it?
Well, it just built last year, so we moved in last fall.
Okay, so you at least got a few months before.
Like this. Yeah, and we plan to show this building to you, but maybe next time.
Yeah.
So it's officially time to start the.
Okay.
I don't know whether I can just start or. Yeah, Kevin is absent, or Kevin is here. May I just start introducing speaker? Maybe. Seems yes. Daniel, are you ready to start?
Mm-hmm.
Okay, so welcome everybody. Today it's our pleasure to have Daniel Gottesman. Actually, his colloquium talk was scheduled last spring, but he was kind enough to visit us virtually without enjoying nice New Mexican foods this time. He got PhD in 1997 in Caltech, and soon after he became faculty member at PI. He is a leading researcher of quantum error correction code, and this subject is very important for quantum computation because this is kind of the theoretical background to justify why we might be able to build real quantum computer in practice. So this is kind of our counter argument against initial perspectives to somehow build realistic quantum computer. He's an excellent and humorous speaker, in my opinion, and he could talk about a lot of broad topics. Of course, he's expert of the fault-tolerant quantum computation, but also he has a lot of interesting ideas. For example, how we could improve the baseline of telescope, even using quantum entanglement. Also, he has brilliant idea to use even neutrino for quantum computation. If he has some nice slides. Unfortunately, Zoom talk is always bad in the sense that whenever speaker says funny jokes, speaker only hears silence. So I somehow suggest Ivan Deutsch to unmute his microphone whenever he is laughing aloud. So without any further ado, Daniel, please start.
Okay, thanks. Let's.
And I mute myself.
Okay, so so the title of my talk is Fault-Tolerant Quantum Computation in the 21st Century, which of course is a little bit disingenuous because quantum error correction was only discovered in 1995. So that doesn't leave a lot of time in the 20th century for this to be a field. So 80% of the history of it is covered by the talk. But the reality is that those first 5 years were very productive years where we discovered a lot of the kind of foundational properties of quantum error correction and fault tolerance. So anyway, so I have to go over some of that stuff first as background. So first of all, since this is a colloquium, what's a quantum computer? Well, a quantum computer is a computer built out of single atoms or other quantum objects, like small superconductors. And because the atoms store quantum bits, qubits, that can be in superpositions and can have entanglement, they can solve some computational problems exponentially faster than a classical computer. And so we in the field of quantum algorithms, people try to break down some problem that they want to solve into individual gates, which are like 1, 2, maybe 3 qubit unitary operations that represent individual computational steps. And so you have to figure out how to devise your algorithm as a series of these gates. And some quantum gates are quantum versions of standard classical gates, like the controlled NOT gate. And some of them are purely quantum gates, like the Hadamard transform, things that you can't do on a classical computer. So I'm not really going to talk about quantum algorithms. The problem with building a quantum computer, or the biggest difficulty, is that qubits are inherently more sensitive to noise than classical bits for two reasons. So one is that they're very small. So of course, that means that anything that's floating by in the environment that gives it a little bump is very likely to change the state of the qubit, whereas a bigger classical bit is more robust. It needs a bigger hit before it changes its state. But that would apply even if you made classical bits out of single atoms. And qubits are even more sensitive to that than that, because they're subject to something called decoherence. And a classical bit, if you look at it, if you read its value, that doesn't change it. But a qubit becomes entangled when you look at it, or when something passing by an environment, another atom passing by, happens to learn some information about the state of this qubit. And it becomes entangled with the qubit in your computer, and that acts as a decoherence, a dephasing that destroys the superposition, and that's what we need to make it a quantum computer. So the upshot is that we think that in order to build a big quantum computer, we're going to need some sort of error correction and some sort of fault tolerance. So I'll explain what those are. So first, error correction. Well, so it's easy to explain error correction, not in the context of computation, but in a communication scenario. So we have two people, Alice and Bob, who do all of the thought experiments for quantum computing. And Alice is trying to send some qubits to Bob. In this case, let's just say she wants to send one qubit to Bob. And she has some communications channel, but it's noisy. There's some chance that when she sends this qubit through that channel to Bob, that the thing that comes out will not be what she sent. And so the question is, how can they deal with this? How can they send something that's more reliable than the communications channel would allow for just one use? And the solution is a quantum error correcting code. Alice will take her qubit and encode it using extra qubits. So in this case, she's encoding it using 5 qubits. And she sends those 5 qubits through the channel. And each of those qubits has a possibility of having an error on it. But if the error rate is low, it's pretty unlikely that there's more than one error. And these 5 qubits are chosen to be a quantum error correcting code with the property that there's a measurement that Bob can make that if there's any error on a single qubit, Bob can figure out what that error is and correct it. And then the state that he gets out after correcting that state is exactly what Alice sent. Now, of course, there is some possibility of having 2 errors. So the fidelity of what you get through, the error rate is not, the fidelity is not perfect, the error rate is not 0. But if the error rate was low enough to begin with, then that means that the error rate that Bob sees is much lower than the error rate in the channel used just by itself for a single time. So the error correction has kind of improved the error rate and reduced the effects of the errors. Okay, so that's quantum error correction. The problem is that error correction is making a lot of assumptions. So in this case, I assume that Alice could do a perfect encoding of her qubit into these 5 qubits, and Bob could do a perfect measurement. Now, in reality, we're building a quantum computer. We don't have any kind of perfect computation. Everything that we do has the possibility of error. And so the encoding procedure and the measurement procedure, the error correction procedure, they are also subject to errors. And so we need to upgrade our error correcting code to have some way of doing the encoding in a way that's resistant to errors, that's fault tolerant, and a way of doing the error correction in a way that's fault tolerant. And moreover, Alice was just sending the qubit to Bob, and Bob was trying to get out the same state that Alice sent. And to do a computation, we want to be able to do quantum gates on the qubits while they're encoded, right? If we were to decode the qubits and then do a gate and then re-encode, well, they would be vulnerable to error while they were decoded. And so that's no good. So we need some way to change the state in a controlled way, according to a quantum gate, without actually decoding it. So that's the sort of stuff that was worked out in the 20th century. So we designed fault-tolerant protocols quantum error correcting codes were invented. We designed fault-tolerant protocols. And the fault-tolerant protocols in the 20th century mainly used a couple of techniques of transversal gates and magic states. So I'll talk more about those later. And we also came up with methods of fault-tolerant error correction that allowed us to do these error correction cycles without even when the gates that were used to do them were not perfect. And in the 20th century, we also invented topological codes, which are so far playing a big role in 21st century fault tolerance, and proved the threshold theorems, kind of the capstone of 20th century fault tolerance and really of all of the theory of fault tolerance. And what the threshold theorem says is that if the error rate per gate and time step is below some constant threshold value, P sub t, then reliable quantum computation is possible with overhead, which is a polynomial in the log of the size of the computation you want to do. And so what that means is that if you're an experimentalist trying to build a quantum computer, all you have to do is you have to get the error rate in your system below this threshold value. And once you've done that, the software can kick in, and by making enough qubits, which is not too much bigger in terms of asymptotic results anyway, then the computation that you want to do, you can do that computation with arbitrarily low logical error rate, even though your individual gates are all failing with some probability. Okay, so this is kind of the existence theorem that says that quantum computation should be possible in the real world. Of course, there's some assumptions in this theorem about the kinds of noise that it's subject to, but they're really quite weak assumptions. And so I'm pretty confident that in reality, this will hold true. So there's a lot of more stuff to say about the threshold theorem. Some of that I will get to in a minute. But I just wanted to comment, I guess, that this threshold value is kind of some constant of nature. That's a little bit inaccurate in the sense that there's a lot of different threshold values depending on kind of exactly what the assumptions are, what properties your quantum computer has. Like if you have only nearest neighbor gates in 2 dimensions versus nearest neighbor gate in 1 dimension or long range gates, the threshold value can be different. But in some sense, this threshold value is a constant of nature that kind of tells you, I mean, to the extent that we know it, that quantum computation is possible or not possible. Okay, so what is the value of this threshold? That's really important because, like I said, the experimentalists have to get their error rate below that level in order to build a big quantum computer. And so the earliest estimates, 20th century, very early, well, not early 20th century, but early in the history of error correction estimates, we're giving numbers like 10 to the minus 6, so 1 error per million gates. And that's pretty low, not maybe totally unachievable, but it would be a very high bar for the experimentalists to clear, or maybe a very low bar would be a better way of saying it, since it's a low error rate. But improved protocols developed in the 21st century show that that's not right, that was just the first estimate, and we can actually do much better than that. So if you're willing to have tons and tons of extra qubits, and the errors are pretty, kind of boring, straightforward type, depolarizing channel, then some simulations show that you might be able to get up as high as 5% error rate. There's only 1 error per 20 gates, and that's totally achievable. There's lots of systems that have done that. But that assumes, ridiculous numbers of qubits. Is not a very practical protocol. For that kind of protocol, we can prove rigorously that the threshold is actually at least 10 to the minus 3. So the simulations might be missing something. The proofs, well, they have to make some assumptions, but they cover a much wider range of possibilities. But as I said, that's just kind of a proof of principle. It's not a practical protocol. But more realistic protocols using the surface code, which I'll talk about some more later, still have thresholds that are much, much higher than 10 to the minus 6. So it looks like the threshold is maybe around 0.7% for these protocols. So that's a little less than 1 error every 100 gates. And so that's more challenging than 5% to achieve, but it does seem doable because the best quantum computers that we have now are in that ballpark. So I should say that these numbers that I'm giving for the simulation are for a very simple type of errors, which I mentioned, the depolarizing channel. And the polarizing channel basically is, with some probability, the qubit is fine. And with some probability, there's an error, which could be any arbitrary single qubit error on that qubit. And so that's a very simple symmetrical type of error. It's something that theorists like to study, but doesn't happen too much in the real world. And of course, the real world errors are much messier, but we can prove that there does still exist a threshold for very general kinds of errors. Not the most general kind, but a wide variety of errors that kind of only affect a few qubits at a time, rather than some massive correlated error that affects all the qubits. And this even includes errors that are correlated in time, some non-Markovian errors, where there's a persistent environment that interacts with your quantum computer and does so repeatedly over the course of the computation. Okay, so of course, the thing is that once we start to look at these other error models, then the threshold numbers that I was giving you don't necessarily apply. So in particular, one open question is what's the actual threshold for these non-Markovian errors, or even for simpler errors, which are coherent errors, which are kind of really using quantum effects in the errors as well as in the computation. So what's a coherent error? Well, so in a coherent error, so let's first talk about a stochastic error. So a stochastic error is kind of a probabilistic error, right? Like the depolarizing channel. So with some probability, the qubit is fine, nothing happens to it. With some probability, there's an error. A coherent error is something like an over-rotation. You're trying to do some pulse that rotates the qubit, and you just rotate a little bit too far, okay, by some small angle theta. The problem is that when you do this multiple times, those angles build up. And so, for instance, if you do it 3 times, the angle is now 3 theta, if it's always in the same direction. And Born's rule says that the probability of an error is the square of the amplitude. And so we had an angle of 3 theta, which means an amplitude of about 3 theta of the wrong state. And that means that the probability of error is about 9 theta squared, which is 9 times the error you got from a single rotation of theta. And why is that a problem? Well, that means that as your computation goes on, the probability of errors is kind of increasing quadratically with the number of gates you do, at least until you do error correction and clean things out. And so that affects the threshold, because that means that you can do fewer gates before the errors build up to the point where you would not be able to correct them. And so that corresponds to a much lower threshold value. So for instance, if you had a proof that was 10 to the minus 5, it would come out to more like 10 to the minus 10 threshold. So 10 to the minus 5 for stochastic errors would be more like 10 to the minus 10 for coherent errors. But that's a kind of a pessimistic worst case thing. And it might just be an artifact of the way the proof is constructed, and having to think of the worst possible thing that could happen. The reality is that the fault-tolerant protocol, first of all, in order to get this, you need to be doing the rotation the same way every time, right? So if sometimes you're rotating this way and sometimes you're rotating back the other way, then you get kind of a random walk, right? And instead of after, n steps, you've only got an angle of square root of n times theta. And then when you square that, that comes to n theta squared, which is just what you get of having n stochastic errors occurring independently. And it may well be that the fault-tolerant protocol, just by its structure, where you're constantly interacting your quantum computer with other qubits to measure the errors, kind of naturally does this. But it's really an open question what the actual value of the threshold is, numerical value, for coherent errors. So there have been some simulations, but it's difficult to do simulations for kind of general quantum errors. And so the question is not really settled. And right now it looks like the threshold for coherent errors might be a little bit lower than it is for stochastic errors like the depolarizing channel, but maybe not dramatically lower. So that's another thing that I think we'll get a better understanding of as the 21st century goes on. Okay, so another kind of open question that you might look for out of 21st century fault tolerance is there a way, I mean, to take advantage of extra information you might know about the noise in the system, the errors in the system, in order to improve the threshold? And by and large, the answer is no, okay? There's kind of one case of errors, which is pure dephasing errors, where we got superpositions that kind of tend to decay as superpositions, but you don't get bit flips. And this is certainly a common type of error in real systems. And people have invented some protocols that can see an improvement for dephasing errors, get a better threshold if you have mostly dephasing errors. The thing is, these protocols are a lot more complicated than the regular protocols, which are already pretty complicated. And they only give kind of a modest advantage. And the kind of the reason for that is that that it's hard to get much advantage out of protocols designed for specific errors. Is that whenever you do a quantum gate, it modifies any errors that have already occurred in the system. So for instance, if you do a Hadamard gate, well, the Hadamard kind of interchanges the poly X basis and the poly Z basis. And so if you had, before you had a Z error, a phase flip error, like you get in these dephasing errors, and you do a Hadamard, now it's an X error, which is a bit flip error, okay? And so if you have a code that's only designed to correct phase errors, and you do a Hadamard gate, then now you have bit flip errors all of a sudden, or at least the possibility of bit flip errors. And your code doesn't correct those, so you're kind of out of luck. So if you want to get around this, the best thing to do is to use gates that will not change the errors into different types of errors. And that's very limiting. And that means that you have many fewer gates available and many fewer options for how to build your fault-tolerant protocol. And that makes it difficult. So that's why it becomes so complicated. And complicated means that there's extra gates and extra qubits. And that in turn means that there's more things that can go wrong. And so that kind of makes the fault tolerance worse. So on the one hand, you have a better code that's good at correcting this type of errors. On the other hand, you have a more complicated protocol. And these things kind of fight, and the upshot is that you only get a small advantage by doing this. So I would point out some recent work from last year that at least for certain kinds of systems has shown that for dephasing errors specifically, that you can use a slightly broader variety of gates, which is welcome and makes the protocols a bit better. But beyond the dephasing model, we have basically nothing. So for, if you know that there's some noise model, but it's not, depolarizing, it's not dephasing, you have very little idea of how to customize your fault-tolerant protocol to take advantage of that extra information. Okay. So that's, again, something that I think is going to be a subject of further research in the 21st century. Okay, so a lot of the 21st century fault-tolerant research to date has focused on the surface code. And the surface code has kind of emerged as one of the leading, well, I should really say the leading candidate for building a big quantum computer. Fault-tolerant protocols based on this. So what is the surface code? Well, I'm not going to go into details about it, but basically, the surface code is a topological code. And in the surface code, you can encode your logical qubits, your encoded qubits, using defects in a lattice of qubits. So the qubits are arranged in 2 dimensions. That's one reason why this is a very nice code to use. And you'll have constraints on the qubits, and that's what forms the error-correcting code. But in some places, you relax those constraints, and you have holes, as in the picture. And the holes are used to encode the qubits. The qubits are encoded not any specific place, but they're spread out over this whole system in such a way that in order to change the state of a code, you have to do something that's topologically non-trivial. You have to do something that's a loop around one of the holes or a line between the 2 holes. And because it's topological, it doesn't matter exactly the shape of the loop so long as it goes around the hole. doesn't matter exactly whether it's a straight line or a curvy line, so long as it doesn't go around any extra holes, only between the two holes that you're interested in. And so one way to do gates in these codes is therefore to move the holes around in a topological way. So we can move the defects by rearranging the local constraints. So whereas before we had local constraints over here and none over here, then that formed the defect, we can kind of relax some of the constraints here and impose extra constraints here by measurement. And that will move this hole over. And by moving the holes in such a way that they go around each other, you can do some changes in the logical state because you've done something topological. So that's something that's very unlikely to happen by accident, but you can do it deliberately through the appropriate series of operations. And so the surface codes have been popular for building fault tolerance because, as I mentioned, they have a very high threshold and they work well in 2 dimensions. And the overhead is not so great, the number of extra qubits, but it's not so awful. Okay, so that topological codes and improving them continues to be a big area of research in the 21st century. So the next thing I wanted to talk about, another development of the 21st century, is different kinds of fault-tolerant gate constructions. Because in order to build a fully, design a fully fault-tolerant protocol, you have to combine a bunch of different pieces. And the different options that we have available give us more options for designing better fault-tolerant protocols. So how do we design a fault-tolerant gate construction? Well, the main thing that we have to worry about here is error propagation. So what do I mean by that? So suppose we do a 2-qubit gate interacting 2 separate physical qubits of this computer. Well, if there's an error, first of all, if there's an error during the gate, that could mess up both of those qubits. But moreover, even if the gate itself is perfect, if there's an error in one of those qubits, it can propagate along the gate into the other qubit involved in the gate. Okay, that means that even if we just had a single error on a single qubit, after we do a sequence of gates, that error can spread to infect more and more of the computer. And if we're not careful, it can infect a lot of different qubits before we're able to deal with it. Maybe more qubits than our error correcting code can handle. So that would be a big problem. So the solution to this, well, the simplest and standard solution to it is something called transversal gates. So the transversal gates will take 2 error correcting codes with the same number of qubits, and we'll line up those qubits as in the picture, okay? And we'll only do gates that interact the first qubit of the first code, so kind of a block of the code, with the first qubit of the second block. And the second qubit with the first block with the second qubit of the first block, second qubit of the second block, third qubit with the third qubit, fourth qubit with the fourth qubit, and so on. And what that means is, well, it's still true that errors can propagate from between these qubits, say from this qubit into this qubit. And so instead of 1 error, we'll still have 2 errors. But the thing is, each of them is in a separate block of our error correcting code. And so if our error correcting code is designed to correct just a single error, then it can correct an error in each block of the code. And so before, we had the error propagate into 2 qubits, and there would be 2 qubits in a single block we couldn't correct. 1 qubit in the first block and 1 qubit error in the second block that we can correct. And so the transversal gates still allow the errors to propagate, but they propagate in a way that's kind of controlled and compatible with our error correction abilities. Okay, so transversal gates are great. They're very simple to do, and they handle this error propagation problem. But the problem is, unfortunately, we can't build all of our gates out of transversal gates. It turns out there's no way to have a universal set of quantum gates that are all transversal, where universal means that you can multiply them together to get arbitrary unitary transformations or close to arbitrary unitary transformations. So that means that in order to build a real quantum computer, we're going to need some kind of more complicated construction. So the 20th century to this solution to this problem, which is still an ongoing concern, is using something called magic states. So how do these work? So, so magic states are based on an idea called quantum teleportation. So quantum teleportation, if you're not familiar with it, again, we can talk about Alice and Bob. So Alice controls a qubit psi, and she wants to send this qubit psi to Bob. Now, one way to do it, if they have a quantum communications channel, is to just send it over that channel. That's kind of what we talked about earlier with the error-correcting encodes. But another way is supposing they don't have a quantum communications channel, but sometime in the past, they shared a particular entangled state called a Bell state. So suppose the state is 0, 0 plus 1, 1. Alice has the first qubit of that, and Bob has the second qubit. Then they only need a classical communications channel. What they can do is Alice can make a measurement, a 2-qubit measurement, called the Bell measurement, entangled measurement on her qubit that she wants to send in the state psi, and the first qubit of this Bell pair. And then it's a 2-qubit measurement, so she'll get 2 classical bits out of this, and she'll send those 2 classical bits to Bob. And Bob, depending on what those 2 classical bits are, will do one of the 4 Pauli matrices, I, X, Y, Z. When he does that, he gets back exactly Alice's state psi. Okay, so how do we use this to do gates? Well, suppose that Alice and Bob wanted to do the gate U on the state psi. So one thing they could do is they could teleport from Alice to Bob, and then Bob could do the gate U. And then, of course, what they get out is U psi. Now, that's pretty dumb because they haven't simplified the implementation of U at all. They've made it more complicated by adding this teleportation step in between. But by looking at this quantum circuit, you can say, well, what happens if Bob gets impatient? And instead of waiting until after he receives the classical bits from Alice, he just does U right away. Okay? Well, that means that after he receives the classical bits, he should undo U, do the Pauli, and then do U again. So that's the gate U, P, U dagger. Okay, again, this seems kind of dumb. Why would he do that? It's just making it more complicated. But in some cases, U, P, U dagger is simpler. Well, it might be, you know, another Pauli matrix, depending on what U is, or it might be something more complicated than a Pauli matrix. But in some cases, it's something that's simpler than U is. Maybe that Bob doesn't have a way of doing U very easily, but he does have a good way of doing U, P, U dagger. Okay, and the advantage of this is that now the state that Bob is getting, Alice and Bob are getting after Bob applies U, is some very particular state which doesn't depend at all on psi. It's the state I tensor U 0, 0 plus 1, 1. And so if they have some way of making that state, now they don't have to do the gate U anymore. They just have to make the state and then teleport and then do the UPU dagger. Okay, and so this special state is called a magic state. And this protocol that does teleportation to do the gate U is called the magic state injection procedure. Okay, so this protocol kind of breaks up the process of doing a gate into the process of making the magic state and the process of teleportation plus UPU dagger. And we're assuming that the teleportation plus UPU dagger, we kind of have it down. Maybe we can do those by transversal gates in a fault-tolerant way. But how do we make the magic state? Well, that's a difficult task, okay? And that's something that people have worked pretty hard to try to figure out good ways of doing in the 20th century and the 21st century. So one of the first kind of really good ways of doing that is something called magic state distillation. Well, really good is too strong for reasons I'll get to in a minute. So magic state distillation, what it does is you say, okay, we're going to make many copies of this magic state. Now, the problem is we're doing that in a non-fault tolerant way, okay? And so that means some of them will not be good. They'll be noisy magic states. But there's a way, if we can compare these magic states to each other, that we can tell which ones are good and which ones are not good, okay? And so we can get rid of the bad magic states and keep the good magic states, okay? Or depending on how you do it, you might even be able to correct the errors in the bad magic state and turn them into good magic states, okay? So the upshot is that we can take many noisy magic states and get out one good magic state that's reliable and that's safe to use in our fault-tolerant computation. And that makes it a fault-tolerant protocol when we use it. But you can kind of see the downside of this, which is that we're comparing a lot of things and we're discarding many qubits that were parts of magic states that had noise. Even if there's no noise, actually, the protocols tend to be pretty inefficient and end up using up a lot of qubits. So these magic state distillation protocols are pretty good in the sense that they work with relatively high error rates in the system. But they're not particularly efficient in terms of how they use the qubits. They're kind of theoretically equivalent in an asymptotic sense, but in terms of practical numbers, you need to use a lot of resources to do magic state distillation. So, so consequently, there's been a lot of research over the past decade or so on ways to reduce this cost. So one line of research is to just come up with better magic state distillation protocols. And there's been significant improvements in those. So another line of research, which I think is kind of underemphasized, but is something that I would like to see more of going forward, is to understand the kind of mathematical structure of these magic state distillation protocols and of the magic states themselves and the gates that they're good for. And understanding this mathematical structure would give us a better understanding of how magic state distillation works, how magic states work, and hopefully would give us some insight on how to design much better protocols. So another avenue of research on magic states is to try to bound how well we can hope to perform with magic state distillation. And maybe that will inspire us or give us some guidance as to how to make better protocols. And we do that by developing some sort of resource theory to quantify how much magic is in these magic states. And one nice thing about this idea of resource theory of magic is that you get to use all sorts of funny names for things. Like, so I wrote one of the first papers on that, and we had the mana. Other people have used other kinds of magical notions. Okay, so then there's a whole separate line of research is coming up with different ways of doing gates, fault-tolerant gates that don't involve magic states. And so there's a whole variety of ideas known. There's ideas using subsystem codes. There's ideas using switching between different quantum error correcting codes. There's ideas using concatenation. There's ideas using non-transversal gates in a very controlled way so that you can keep track of where the errors are. And so some of these, you know, on the face of it, seem to have much lower resource cost than magic state distillation. But usually they come with costs of their own. They might work at low error rates. They might use codes that are very inefficient. And so you can't really just look at one and right off say, oh, that's clearly better. You have to look at a much more complicated system. You have to look at, in fact, the whole fault-tolerant protocol, because the fault-tolerant protocol is made up of many different parts. And sometimes these parts can interact in ways that are hard to predict without careful study. And so in order to really understand kind of what the best fault-tolerant protocol is, you have to put together all these pieces and figure out how it performs. And then if you change one thing, that might make some dramatic difference in performance. So you can't just say, you know, this gate construction is the best, let's use that. This error correction procedure is the best, let's use that. This code is the best, let's use that. You have to get them all working together and figure out how to make that work. So that's kind of a big long-term project of optimizing these fault-tolerant protocols. But it's important to have lots of different tools that we can put into, so there's many options for how to put them together. Okay, so another thing that's coming, hopefully in the next few years for fault tolerance is experiments. So experimental systems that you see in the real world now have error rates that are kind of in the vicinity of this threshold that I mentioned. And so we can hope that fault tolerance can actually improve those error rates to give us logical qubits that are much more reliable than the physical qubits and the physical gates that we're using. So there have been some kind of preliminary demonstrations of fault-tolerant circuits, but they didn't really demonstrate a convincing improvement in the error rate. So in my mind, the question of a fault-tolerant experiment is yet to be really done in a way that's fully convincing. In principle, it's possible to do a fault-tolerant experiment with actually surprisingly few qubits. Even though these fault-tolerant protocols are very complicated, you don't really need to have a full fault-tolerant protocol to demonstrate fault tolerance. You need to have just a few basic components. And you can do that using a 4-qubit error detecting code plus 1 extra qubit known as an ancilla qubit. And so you can have 5 qubits. Those qubits could be arranged in a circle. And using that, if you have low enough error rates, you could show kind of in principle some improvement in the error rate using fault tolerance. Another thing that's, because right now the number of qubits is severely limited, it's also very interesting to just think about how many qubits you really do need to do fault tolerance if you want to conserve as much as possible. And so it turns out that you can be fault tolerant with only a few extra qubits beyond the ones used in the code. You only need a few of these ancilla qubits. And that's pretty useful because the older protocols use lots of extra ancilla qubits, and that meant that fault tolerance demonstrations were further away. Now it may well be that the first real demonstrations of fault tolerance use codes that are much bigger than this 4-qubit code. But you can ask, what is the goal? What should they try to show that they really have a fault-tolerant system in this experiment? And the idea is that you should run some family of circuits, and you run them in an unencoded way on your computer, and you also run them in an encoded way using your fault-tolerant protocol. And the error rate for the encoded circuits should be lower than the error rate for the unencoded circuits. That's what it means to be fault-tolerant, that the encoding is actually showing you some improvement in error rate. And I want this to be true for all circuits in the family, because that's showing that your fault-tolerant protocol is really protecting all the components of your circuit, right? If it's just true for some circuits, that might mean that the protocol is fault-tolerant for some gates, but not for other gates. And then you're seeing an improvement only in the circuits that use a lot of those gates. So we really want to do it for the full range of things in the circuit, and that means all different possible circuits you can make in this way. Okay, so yeah, so another thing that's really exciting, I think, about this possibility of fault-tolerant experiments is that, normally when people do quantum computing experiments, what they're learning about is how to build a quantum computer. And the demonstrations, when they run some algorithm or something like that, are not really telling us anything new, except this system actually is controlled well enough to do this experiment, right? But fault tolerance experiments are starting to get beyond that. And of course, once you have more and more qubits, you can hope to learn other kinds of new things. But a fault tolerance experiment actually lets you learn something very important, which is how the real experimental errors interact with your fault-tolerant protocol. And that's something that can't be answered purely by theory, because theory doesn't know about the real experimental errors, except what the experimentalists tell us. And so that means that if there's kind of subtle errors that the experimentalists don't know about, the theorists can never answer that question by themselves at all. But moreover, kind of simulating some of these fault-tolerant protocols can be very difficult on a classical computer. So in particular, questions like, what is the threshold for coherent errors that I mentioned earlier, right? I said simulations were hard. But a quantum computer, like a real experimental quantum computer, probably has coherent errors, probably has non-Markovian errors. And while I can't answer the general question, do coherent or non-Markovian errors ever hurt, they can say, well, in this particular experiment, the coherent and non-Markovian errors don't appear to be causing a big problem. The error rate is kind of in line with what we expected in terms of the threshold. So that's kind of an interesting theoretical question that could be answered by experiment. And of course, the main thing you want to know is, can you build a quantum computer at all? And is the system going to do it? And there are, believe it or not, still some skeptics out there that question whether we could build big quantum computers. And demonstrating, convincing fault tolerance, well, some of these skeptics I don't think will ever be converted, but it should help reassure the rest of us that believe that quantum computers should be possible, but there's still some niggling doubt that we can quiet that doubt. Okay, so one thing that I would like to see coming out of these experiments is something more that will kind of help us both guide how the experimental process should develop and help us understand as theorists how fault-tolerant protocols interact with real errors. And that's a way to extract from a fault-tolerant experiment a kind of a quantification of how much error in this experiment is handled well by the fault-tolerant protocol and how much is handled badly. So for instance, by handled well, I mean things like depolarizing errors or other stochastic errors, where we expect the fault tolerance to take care of them in a certain way. Okay, but again, the coherent errors, they might be more of a problem. Correlated errors might be a problem. And there might be some other things like that that are not handled as well. They may be corrected by the error correcting code and by the fault tolerant protocol, but not as efficiently as we would like. And so, you know, that information is kind of present in the results of the fault tolerant experiment. It's not so clear how to get it out into two numbers. But that's something that if we can figure out a way to do that, I think that would be very interesting and lead to a lot of progress in terms of understanding fault tolerant protocols and how to build quantum computers. Okay. Okay. So, so another topic of 21st century fault tolerance is reducing the overhead. Now, I talked already about, you know, reducing the number of qubits you need for magic state distillation or using other gates. But nevertheless, even if you can kind of get rid of magic state distillation, the surface code, while it's kind of efficient in principle, is not that efficient in practice, right? You still, in best case, you're still going to need hundreds of physical qubits for every logical qubit. Now, as you scale up to bigger and bigger quantum computers, that ratio grows, and it's theoretically efficient in the sense that it doesn't grow too fast. It only grows as some polynomial in the log of the size of the computation you want to do. So really, really big computations only require a little bit of extra overhead. So overhead here is the ratio of physical qubits, the number of actual real qubits you have in a computer, to logical qubits, which are the ones where you can do your computation. So, but you know, even though it's theoretically efficient, in practice, having to, you know, use 500 physical qubits for every logical qubit means you're kind of not fully utilizing your computational space to the way you'd like, right? If you can build 1,000 physical qubits, that sounds pretty good. It's way beyond what we can do today. But, you know, if 500 of those go to each logical qubit, it's only 2 logical qubits, and that doesn't let you do anything very interesting on the logical qubit side. So we'd like to do much better than that. So we can ask, at least in principle, how low can the overhead be? And the answer is it can be arbitrarily low. It can be an arbitrarily small constant. We can still have a threshold, and the number of extra qubits we need, the ratio of physical qubits to logical qubits, can be very small. Now, in order for that to be true, if you really want that constant to be very small, by small I mean close to 1. Obviously, it can't be less than 1. But if you really want to be very close to 1, then the threshold is going to have to go down, of course. So there's a trade-off between the threshold error rate and the rate you can achieve. But even for relatively large error rates, in principle, it can be quite small, much smaller than the overheads that we have the favored protocols today. Now, there's in order to make this work, you need to use some more efficient quantum error correcting codes. The surface codes are just not very efficient codes. And in the context of communication, where we introduced error correction, it's known how to do this, right? You can have codes that encode many qubits in a single block of the code, with only, you know, a small ratio of physical qubits to logical qubits, and yet still tolerate errors with a constant rate per qubit and have an arbitrarily small logical error rate. Okay, so you don't have to trade off overhead as your computation, as your communication, the number of qubits that you're sending for communication gets large. But you can, and it turns out that you can do the same thing for fault tolerance, but you can't just use arbitrary codes that are efficient for computation, for communication. You have to use something called a low density parity check code. So what's that? So a low density parity check code is a code that's defined by a bunch of constraints on the qubits. And each constraint in an LDPC code, LDPC stands for low density parity check, each constraint affects only a constant number of qubits. So in order to measure the errors in the computer, you're measuring whether the constraints are satisfied or not. And each time you do that, you only have to touch a constant number of qubits, you know, some relatively small number, even for a very big code. And then each qubit is only involved in a constant number of constraints. So you don't have to touch each qubit very many times. So surface codes are actually an example of an LDPC code because they have local constraints in 2 dimensions. And so that means that any one qubit is only talking to the qubits around, it's only in constraints with the qubits that are near it. So that's a limit to the number of constraints you have on each qubit and a limit to the size of each constraint. But surface codes are LDPC codes that are not very efficient. And there are other LDPC codes that are much more efficient than that. That's something that's kind of another active area of research, is trying to figure out how to make a good, efficient fault-tolerant protocols using LDPC codes. So one family that seems very promising right now is a family called expander codes. So these are codes built around something called an expander graph, which is a graph that very rapidly connects. So a graph, remember, you have some nodes, dots, and some edges connecting those nodes. And the expander graph is a graph where you can very rapidly get from any node to any other node by traveling along the edges of the graph. So if you have a small section of the graph, there's many edges that go outside that section. So it turns out that this family of codes seem to have a pretty reasonable threshold for error correction. We haven't done the full fault-tolerant analysis, so that might hurt it. There seem to be some options for fault-tolerant gates, and moreover, there's some good classical algorithms for figuring out what the errors are. So it's called the decoding algorithm. This is actually a big problem in error correction, where you make some measurements, and those measurements, in principle, have enough information to tell you where the errors are. But figuring out actually where the errors are, that can be a very hard computation. And so you want to use codes for where that have special properties that make the computation not so hard. Ideally, it should be really easy, but you can't always get everything you want. So, so this seems like a very promising area because the overhead for these expander codes is much, much lower than the overhead for surface codes. And so there's some hope of using them to build protocols that are much, much more efficient than the existing protocols. Now, again, this is a kind of ongoing research. So there's some drawbacks to them. So the big drawback, and we don't know a way to get around this, is that these codes seem to require long-range gates. Because in order to have a graph that's connecting qubits, no matter how far apart they are physically, well, you have to have edges in the graph that are actually connecting far apart qubits physically. There's just no way around that. Well, there might be a way around that, but we don't know it yet. So that's something that's kind of a drawback, but it might still be worth it. There's some systems, for instance, photonic systems, where sending qubits all the way to the other side of the computer is not such a big deal. And then there's some other caveats of things that need to be improved about this protocol. So, so for instance, there's a theoretical result which says that, yes, we can achieve an overhead that's just equal to the overhead of the error correction code, which is reasonable. But that result only applies for systems that are very, very, very large. And so we need to have codes that work at kind of modest size, the size of near future quantum computers, that still have low overhead. So that's something that still needs to be done. And like I said, we haven't fully analyzed the fault-tolerant protocols for these codes. So it might be that a lot of the advantages disappear when you do that. And another thing is that this current protocol does not work very well for parallelism of gates. And so that's a drawback as well, although maybe not quite as severe one. So anyway, so to conclude, we can kind of dream of what comes in the future for fault tolerance. And there's really a whole other area of research involving quantum error correcting codes, which I didn't talk about at all. And so we can also hope for more improvements from that. So that's the area of applying the theory of quantum error correction to other areas of physics. So for instance, topologically ordered systems is a big area of study in condensed matter. And it turns out that they're very closely related to quantum error correcting codes. And the study of quantum error correcting codes came up with a whole new kind of topological ordered system called fractons, which is a big area of research by itself. And it turns out that quantum error correcting codes are also very useful for studying ADS CFT. So that's another big area of research that, again, I haven't discussed at all. And so one thing we might dream of is to apply fault-tolerant ideas to these systems as well as just error correction. Okay, but of course, focusing more on the content of the talk, what we really be looking for is kind of the perfect fault-tolerant protocol that has a lot of different properties at once. So we want ones that use very good codes that have very low overheads, efficient use of qubits, and they also have good error tolerance and good classical decoding algorithms that allow us to figure out what the errors are. We want better fault-tolerant gate constructions that don't require very many extra qubits and also don't hurt the error tolerance of the protocol very much. And we'd like to do all of this with minimal extra connectivity. So for instance, ideally, we'd like to be able to do it in two-dimensional systems with nearest neighbor gates. So it's not clear if this ideal fault-tolerant protocol exists at all, but people, constantly working on this and making small or large improvements that give us some hope that we can do much better than what we have now. And at the same time, we can dream of substantial experimental progress. From a theorist point of view, it would be very welcome if the experimentalists, even though their gates are now kind of at the level where you could hope to use the threshold theorem to improve, it would be better to have even lower error rates. And that's because that allows you more options for fault-tolerant protocols, which can then, reduce the overhead or have some other nice properties that give you a better implementation. Another thing on my wish list, as I said, is a way to understand the way errors interact with experimental protocols. And that would be very useful for answering some of these theoretical questions. It would be nice to get experimental answers to these questions that we're asking. And then finally, of course, the ultimate dream, which combines theoretical and experimental progress, is to make a working, large-scale, fault-tolerant quantum computer. So thanks.
Thank you, Daniel. So we have few time to take questions. So please raise hand here, and Daniel, if you like, you can just pick up. If you can see the list of participants, we can see who are raising hands right now. And I'm pretty sure Daniel is happy to take both basic and technical questions. So maybe Ivan, you may start.
Right, I think I'm unmuted. So Daniel, I wanted to come back to a point earlier in your colloquium about the question of how to use what we know about the errors in the physical gates or physical implementations to better create quantum error correcting architectures. So in particular, I mean, most implementations will have some real bias of some kind. Like, for example, in the kind of cat codes that are being used in the Yale group for their kind of superconducting implementations, they have codes that are designed to deal with one and dominant source of error, which is photon loss. So is it, in your opinion, a good strategy to think about a layered approach where you might say, I'm going to build a quantum error code that first strips off the massive error and kind of makes that qubit, that encoded qubit, a kind of effective depolarizing error, and then encode on top of that? I mean, can I have a layered approach? Is that a good strategy?
Yeah, that's a good strategy. It may not be the best strategy, though. So actually what that boils down to is a concatenated code, which is kind of one of the very first things that people considered for fault tolerance. And concatenated codes tend not to be the best in a lot of ways. What they are is very simple. And so if you really have one error that's much bigger than anything else, that might be a good way of dealing with it, if you can come up with a code that corrects for it. In the case of those cat qubits, they're kind of mostly worried about a dephasing sort of error. So that's the one specific case where we can see some improvement by doing this. If it's some other kind of error, then that's probably not going to work. Now, I could also say that that in a lot of cases, when there's one specific type of error that's causing problems, there may be other solutions, right? Because you can say, well, I'm going to work on my system to re-engineer it to reduce that problem. So, you know, there's some of each that you want to do. But really what we'd like to do is kind of a more holistic thing where we say, well, okay, this error is present. It's a big component, but these other errors are present also. And there's always going to be other errors present. And we want to kind of try to deal with them all at once while, you know, taking advantage of the knowledge that this one is more common than the others. And that's the thing that we really don't know how to do.
Thanks.
Other questions?
I see.
Kevin Cahill, are you raising a hand physically?
Yes, I am. I just have a very elementary question. What is the largest integer that has been factored by an actual quantum computer?
I don't know the answer to that. I think mostly people have not really been that interested in implementing Shor's algorithm on their bigger quantum computers. I mean, in the past 5 years, quantum computers have probably gone from, you know, 10 to 20 qubits to the biggest ones are you know, 50, 70, something like that qubits. So that in principle could allow you to factor much larger numbers, but somehow people are not really that interested in implementing Shor's algorithm. And part of the reason for that, well, there's a couple of reasons for that. Part of the reason for that is that, you know, if you have the first demonstration of Shor's algorithm, that's an exciting thing that can get you a Nature paper. If you have the 10th demonstration of Shor's algorithm, that's not so exciting and probably won't get you quite as much publicity. So I don't know the answer, but I suspect it's probably still, you know, on the order, something less than 100, I would think.
21 was the last estimate I heard, but that was about a year.
It's possible. I think there have been bigger demonstrations than that, but I'm not sure.
Okay. All right. My feeling, frankly, is that this whole field is more hype than reality.
Well, I think I disagree with that. I think there's a lot of reality. There's also a lot of hype. I can't disagree with that statement. But the progress that we've made both theoretically and experimentally has been quite substantial over the past 25 years since it became a serious concern. And I should say that one thing that's become very interesting is this idea of using quantum information ideas in other fields. And that's something that means that even if we never succeed in building a quantum computer, that means that it's not wasted, right? We still have those ideas and they still can be useful in deriving all sorts of other things.
Okay, Andrew Randall.
Hi, Daniel. Thanks for a very nice talk. My question was, I was wondering what your thoughts were about fault-tolerant quantum computing protocols based on measurement-based quantum computing that are being discussed a lot in the context of photonic quantum computing these days.
Yeah. I have various thoughts of them, none of them all that well formed. So, I mean, it's worth noting that this surface code protocol, as I'm sure you know, but most of the audience probably doesn't know, that the surface code protocol that I mentioned and that has become the leading candidate for building fault tolerance right now was originally designed for this measurement-based system where instead of having a series of gates, you have some large entangled state and you make measurements on it in a particular order, adapting to what happened before. And that is kind of equivalent to the gate-based model, although it's not completely equivalent in the presence of noise. So a lot of the protocols that we designed for one of them can carry over to the other. Now, there's some recent protocols, which is, I think, what you're referring to, that it's not quite so obvious how to convert them over into gate-based protocols. but I think probably some of those ideas can carry over to gate-based fault tolerance. And so those things will probably still at some level be kind of equivalent.
Okay, thank you.
Okay, Rafael, Alexander.
Can you hear me? Hey, Daniel.
Yes.
Yeah, now, okay.
Great. Sorry, my mic was off. When I started my PhD, there was very little scope in terms of experiment, at least relative to now. Then towards the end of my PhD, we started to enter the NISQ era, where, you know, one of the steps towards a full fault-tolerant quantum computer maybe would be to demonstrate quantum supremacy or something like this. I was wondering if I could just get your thoughts on these intermediate goals. And there's also one that's sort of come up recently, is to try to get one logical qubit. And that at least feels like a more honest stepping stone towards something fault tolerant. So I was wondering if I could get your perspective about these stepping stones and whether NISQ you thought could really be a route towards that's on the way to fault tolerance, or whether we should be steering as a community a bit more towards these simpler, more modest, less flashy goals.
Okay, I mean, so so that's kind of a complicated sociological question, I think, more than a science question. I mean, I think from the kind of the science perspective, the goal is to build big quantum computers, right? And you know, coming up with NISQ algorithms that work without error correction on modest-sized computers doesn't necessarily advance us in that direction. Now, on the other hand, one thing that's made the progress possible is funding from government agencies, and recently a lot of funding from companies. And a lot of the progress that's been made in the past 5 years or so on building quantum computers has come from companies. And actually also a lot of the theoretical progress is coming from researchers employed by companies. Right now, it's much easier to find a job at a company probably than at a university. Although, you know, when I started, there were no quantum computing jobs at universities. Now there are some, and actually a reasonable number of them. But nevertheless, companies are just kind of snapping everybody up. Those companies, of course, want to see some prospect of profits on a shorter time scale than however long it takes to build a big quantum computer, 20 years, 30 years, whatever, longer if necessary. And so for that, of course, the NISQ algorithms are critical because, you know, it's certainly possible that if you come up with the right kinds of algorithms, you can see results that can actually contribute to science and contribute to business on a much shorter time scale. And so in that sense, that's important too. And I think as a field, we're large enough that we don't have to pick just one or the other. We can do both.
Thanks.
We still welcome basic questions from student, faculty. Is there any question?
I have a quick question. I'm very new to the world of quantum computing, but I was wondering, do you feel that the results of like improvements in fault tolerance will lead us to like a quantum supremacy outcome like within the next 20 years, or do you think it's kind of hard to gauge the timeline for that?
Well, the timeline is definitely hard to gauge. Now, quantum supremacy is a term that's been used specifically to refer to doing just some computation on a quantum computer that would be hard or essentially impossible to do on a classical computer. And I think most people agree that that's actually already been done. That Google last fall, I think, kind of losing track of time now.
Yeah, that's right.
published an experiment that they had done where they did a random circuit, but it was a random quantum circuit, but it was a sufficiently large quantum circuit that it's probably very, very hard to do this on a classical computer. And so in terms of the specific term quantum supremacy, we're already there. So that in that sense, the time scale is easy to predict. It's now. Now, in terms of doing stuff that's actually interesting, well, that's where these NISQ algorithms come in. That people are working on a lot of algorithms that, you know, may not be totally reliable, but don't necessarily need quantum error correction to work. And those might be able to give us some interesting answers on a much shorter time scale. That's much more difficult to predict, but maybe like, you know, 10 years or something. To use fault tolerance and to get, you know, quantum computers that are reliable enough that we can be sure the answers are correct, you know, modulo bugs in the programs, that's a much longer time scale that's difficult to predict. I should say that that for many years, when I, you know, was asked the question of how long until we see a real quantum computer, I would answer by saying 20 to 30 years, on the basis that by then you'll have forgotten what I said. And so I have stopped using that joke, except in this meta form. So that tells you that we have made some progress. And, you know, so I started telling that joke 25 years ago. And we're maybe not quite there yet to where you could say we have real quantum computers, but it turns out to be not that bad an estimate. And I think, you know, 20 to 30 years is still kind of a reasonable estimate for big fault-tolerant quantum computers that can actually do stuff in a fault-tolerant way and give you interesting, useful answers.
Is that also about when, like, we might see them in industry per se, like being used for certain types of research instead of just research on quantum computing?
Well, the hope is that that's going to be on a shorter time scale using these NISQ non-fault tolerant algorithms.
Okay, thank you.
Hi, I have a question on the LDPC codes.
Mm-hmm.
Okay, so are there results when you lay out an LDPC code on a 2D grid and you pay a swap penalty? Do you still have a threshold?
So there are some results about laying down certain LDPC codes on a two-dimensional grid and seeing how many kind of long range, you're kind of trying to minimize the number of long range connections you need. I don't know of any results. Okay, so by this I mean, you know, the relatively high rate LDPC codes. Obviously, the surface code is an example of an LDPC code. You can lay it down in 2 dimensions. But the high rate ones, I don't know of any experiments, or sorry, any results, theoretical results, that have shown a threshold in that case.
What are the block lengths before you start getting a decent code rate?
So I think some of the examples of expander codes have kind of, you know, with 100, 200 qubits in the block, start to see. I mean, it depends what you consider a decent overhead, but they kind of have generally decent performance at starting around at that size, which is, you know, overhead which is much less than the surface code of comparable the same number of physical qubits.
Thank you.
Other questions? So to conclude, I think I should ask this one question on behalf of shy students. So Daniel, your talk is very inspiring, and I'm pretty sure the young students are motivated to learn theory of quantum computation. Tomorrow they'll figure out theory is very advanced because, you know, we worked over 20 or 25 years. What's your advice to a new student to, you know, to just work on this subject?
Well, I mean, so while there's quite a lot that's known, in some sense, this is still a relatively young field. If you compare to condensed matter or particle physics or or really so many other areas of research, quantum computing as a field has, I mean, it's older than 25 years, but you know, the amount of research that was done prior to 25 years ago was kind of very, very small. And all the stuff before 25 years ago, you can learn, certainly. But the result is that there's actually, you know, a reasonable number of accessible, relatively simple questions that you can work on. And of course, you'll need an advisor to help steer you towards those and tell you the things that you do need to do to work on that. But I think there's still, yeah, a lot of scope for that.
Okay, I think that's good advice to a lot of students here. So if there's no further question, let's thank Daniel once again. You know, unfortunately, you only hear me clapping here, and the of course, the people just saying the thanks on the chat. If you could look at. Just I'm asking this colloquium committee, is this just end of meeting or is there anything further? Let's see. Yeah, I think people are leaving, so.
Should be the end of the meeting.
Okay, that's good. So Daniel, thank you very much. And I'd like to catch up at some moment with you. Certainly.
Thank you very much.
I'm just going to hang out for a minute just to say goodbye.
Okay.